You're driving along, sipping your morning coffee, listening to a podcast, and then, bam, you hit it. That single jolt is an enormously expensive problem. American drivers spend over $26 billion every year repairing tire blowouts, bent rims, and ruined shocks. For cyclists and motorcyclists, hitting one of these uneven drops is a severe hazard that causes fatal accidents. We call them potholes. The word actually dates back to the late 1400s, but it wasn't used for roads until 1909. Before that, it described deep, cavernous geological features carved into glaciers and solid rock. Which begs the question, how does a modern street end up resembling a glacial cave? We engineer these thick asphalt slabs to carry the weight of 40-ton semi-trucks. They don't simply vanish into thin air. To figure out what stole that missing chunk of pavement, we have to rewind the clock. We need to visit the scene of the crime months, sometimes years, before the cavity actually appeared. Because if you want to understand why a road collapses, you have to stop looking at the asphalt and start looking at the invisible forces acting deep underground. Our timeline starts with heavy traffic. Asphalt is durable, but it's technically classified as a flexible pavement. Think of it like a thick plastic ruler. When heavy vehicles drive over it, the entire road bends and flexes slightly under the weight. Looking at this diagram of pavement strain, you can see how that downward pressure creates lateral tension at the very bottom of the asphalt. Over time, bending thousands and thousands of times initiates microscopic fatigue cracks deep in the road's base. Those tiny, hidden fissures slowly work their way upward. When the stress finally reaches the top, the surface fractures into tight blocks engineers call alligator cracking. The road might still feel completely smooth to drive on at this point, but structurally it has lost its most important defense. Its waterproof armor is broken. This diagram shows exactly what happens next. When rain falls or snow melts, the water entirely bypasses the fractured asphalt. It seeps straight down, saturating the aggregate base layers and soaking the dirt subgrade below. That waterlogged soil turns into a soft, mushy foundation. A structural trap has been set directly beneath a surface that looks perfectly fine. Now add winter weather to the mix. When temperatures drop below freezing, the water trapped inside the pavement layers turns to ice, expanding in volume. This expanding frost forms an ice lens, acting like a hydraulic press that bows the road upward. But during the thaw, the ice melts. The asphalt stays stuck in its raised position, leaving a completely hollow void beneath the crust. The road is now warmed, waterlogged, and hollowed out. And that's exactly when heavy traffic returns. Looking at this cross-section, you can see the plunger effect in action. Every time a car tire hits the softened area, it squirts water back out through the cracks, carrying fine soil particles along with it. It's a highly destructive positive feedback loop. As more dirt washes away, the void grows wider, it traps even more water, and the pumping action strips away the base layers faster. Ice expansion and traffic pumping have silently carved out a massive hidden cavern underneath our tires. Which brings us right back to the present day. There is now a gaping void sitting directly beneath that cracked, superficially smooth street. You approach in your car, completely unaware. Your tire rolls directly over that thin, unsupported crust of asphalt, and the structural limit is finally exceeded. Under the pressure, the weakened surface caves in, sending chunks of pavement crashing down into the cavern, giving birth to a brand new pothole. The road didn't fail suddenly. It failed from below. This is why roadway crews seem to repair the same spots year after year. Pouring hot asphalt into the hole is a temporary bandage. It fills the gap, but it entirely ignores the destroyed foundation underneath, meaning the crack will inevitably open right back up. Engineers are working to stop the cycle before it starts. Modern highway construction integrates synthetic geogrids. These act like an underground skeleton, mechanically locking the soil and aggregate firmly in place beneath the asphalt, so it can't be washed away. Material science is also pushing boundaries, with researchers experimenting by mixing elements like graphene into the pavement. That makes the surface highly resistant to water penetration and drastically reduces initial fatigue cracking. So the next time your morning commute is interrupted by a bone-rattling thud, remember what actually caused it. That missing chunk of pavement is the explosive final act of a long, invisible war between engineering, water, and time.